We have learned section 6.1, which is testing and estimating the centrality of two samples. We know that we have different statistics to describe centrality of a sample. It could be if we have the same median, mean, quartiles, or they have identical distribution. So using test statistics or scores like UN, TM, TN, right? And in section 6.2, let's focus on median test. Median is one of the statistics that represent or describe the center of a population. It is good or it is robust to skewed data or censored data. But it is not recommended for routine use because of a warning. So what's the warning? Median test has lower power unless it is for a large sample. Even when Pitman efficiency is high, the actual power of the test is still low. So do you still remember Pitman efficiency? It's a way to measure the power of the test, the efficiency of a test. So for median test, sometimes when the Pitman efficiency is high, but the actual power of the test is still low. So that's the warning. So that is why we don't recommend median test as a regularly used test when we discuss the centrality of the data. But somehow the benefits of using median test is it has high Pitman efficiency, of course, and also it's simple. It's very simple, right? Even we have censored data, we have skewed data, we have some long-tailed data. We can still use median test to get some result. Some result makes sense. And even we have some incomplete information, incomplete data. We can also use median test. We don't have to have the measurement values for the observations. We can only have the number of observations in a range or counts of observations above or below a value that we can perform median test. Yeah, so then for the rest of this chapter is we first discuss the median test. Then we talk about comparing the variance of two samples. We have learned that in SPC, and in this course is the first time we talk about testing the variance, testing the equality of variance of two samples. And then we'll learn how to test the distribution, whether two samples have the same distribution or the same distribution family. So given that, let's first learn how to use the median test, the basic test. So first, the method we introduce for testing the median is the basic test. For two samples, we assume that if there is any difference in their distributions, then the difference is only in their locations, which means that we assume that their spread and shape are all the same or are very similar. And if there's any difference, it's all about the different location or shift mean, shift center. So that's the assumption prerequisite for the basic test. So how does the basic test work? It works like this. Given two independent samples, independent samples are different from paired samples, right? So we use independent. Two independent samples, we combine them in one big sample, then compute the common median of the big sample. We use the big M to denote this common median. Then we count how many observations in each sample are above M and below M, and list them in this table. So we have 4 cells in this table, A, B, C, and D. And A means in sample 1, how many observations are above the common median of the big sample. And B is how many below in sample 1, and C and D. Right. So when A plus B, it doesn't have to be the sample size of sample 1, because if there are ties in sample 1, then we only count the different values. If there are repeated observations with repeated values, then we omit them. So A plus B should be less than or equal to the sample size of sample 1, right? Same thing with C and D. All right. Then using this 4-cell matrix, we can calculate the p-value. So let's look at an example to learn how to use it. Example 6-7, it's on page 162. A group of 7 males and another group of 21 females are in this experiment after an initial training in using latex. So both groups were given a test page of mathematical formula to set up in latex. Anyway, it's a mathematical test, okay, after some training. So the time in minutes that each one took to finish the test, to set up the page correctly, is here. 6 males, 15 minutes, 16 minutes, and so on. 21 females, from 8 minutes to 32 minutes, and there are some ties in between. So the question is, do these times here indicate a difference between the median times taken by each gender? Okay, first we combine the two samples and get their common mean. Common median, which is 18.5 minutes. Then we count the number of observations in each gender above and below M. M is 18.5, right? So the number in parentheses is how many observations below M. However, this number 11 is when we exclude repeated values in observations. We exclude ties. So in this way, we can deal with ties. We know that how many in each categories are, how many ties are in each sample, right? And in this way, we given we have the 4 cells number A, B, C, D, they are here, right? And we can use this equation here, P asterisk, to compute the p-value. So the meaning of this p-value is that given there are A plus B observations in sample 1, what's the probability to have A above M and B below M? And also, given there are A plus C observations for A plus C different values above M in 2 groups, then how many of them are from group 1, sample 1, and how many of them are from sample 2? So this is the equation to calculate a probability to just have these 4 values in the 4 cells. And so given that, we can list the, with the p-value equation, we can compute the p-values for different values for cell 1, or the value of A. Here are all the possible values that A can get, right? From 0 to 7. They must be integers because they are counts, right? And then here are the permutation probability of getting each value, corresponding value. So why this is a permutation distribution probability? Because when A equals to this value here, B is determined, right? B is not that determined because of ties, but once we get the sample, we get the data, we know how many ties, then B is confirmed because A plus B is the sample size of sample 1. When A equals this value, then B must equals to sample size subtracts this value, right? But C and D are not determined. There can be different combinations of C and D. When A equals 2, B should be, for our example, B should be 5, right? But C can be any value, and D can be any value. D can be the sample size of the sample 2 subject to the C, right? So therefore, considering all those combinations, here is a probability of the sum of all those combinations of C and D. So this is the permutation probability. All right. And for our problem, because A equals 5, A is equal to 5, right? Yeah. And to calculate a two-tail p-value, we need to sum the probability that A get 5, 6, and 7. That's the upper tail, right? When we sum up this probability, we need to double it. So that's the two-tail p-value of getting A equals 5 or above 5. All right. Since p-value is large, right? Here we get p-values 0.38 something. It's very large. Our conclusion is that there's no evidence against the null hypothesis. The high p-value made us accept the null. But intuitively, by looking at the data, we would rather think the median of the two samples should be different. So the high p-value implies poor performance of the median test. Why is that? Because there are marked discontinuities in the permutation distribution, right? For the permutation distribution table, there are only 8 values that A can get. And for this probability here, there are combination probabilities. So, and also because it's so discrete, there are only 8 values here. When A is 6, when A equals 7, the two-tail p-value is still below 0.5. 0.05, so we can reject the null. But when A equals to 6, the two-sided probability is already exceeding 0.05. We have to, we cannot reject the null. But even A equals 6 or equals 1, it's still a very extreme case. We do not think the two medians should be equal. However, this test gives us the conclusion that we do not reject the null, which means the power of the test is with a question because of this discrete nature. Okay, if we use t-test and Wilcoxon-Mann-Whitney test for this problem, then the p-value would be much lower because the asymptotic result is continuous. If we use R or that exact, the function is the Fisher exact, Fisher dot test function. And it's Fisher's exact test. This test is for the count data. So if we use R, we input that table, the 4-cell matrix in the order of A, B, C, and D, and input this vector as a numeric vector, and we define the number of rows as 2, and it will give us the p-value. So here are more descriptions about Fisher's exact test function. You need this function to do your homework 6 for problem 6.2. You need this Fisher.test in R, and you need to convert that problem 6.2 into a matrix like this to get A, B, C, and D, and then use the Fisher's test to do the problem. All right. So next, Matheson control median test for finding confidence intervals. We skip this part because the test statistic is not good. Why not good? If you have interest, you may read example 6.8 and 6.9 to find out. We're not required this part in this course. So then, normal scores. In the one sample case, we can transform ranks to normal scores and use normal distribution to deal with it. And back in section 352, we introduced the van der Waals or van der Waals unexpected normal scores. For two independent samples, we replace the rank R with joint rank. And using R is easy. It's just this function here, Q norm. Using this, it can return us a z value. So we can get a normal score and use the normal distribution test, t-test and z-test, for two sample median comparison. All right, next, comparing two samples variances. So testing medians or means have dominated inferences for two sample problems. But there is an increasing interest in testing differences in variation or spread of two samples, which may or may not be associated with differences in means or medians. So this is the first time in this course we talk about testing the variance. In SPC, we have learned that F-test is the classic method for testing the equality of the variance for two samples, right? And F-test is the critical value should be with a degree of freedom for each sample and with a alpha value, right? F-test is irrespective whether the mean of the two samples are equal. Here we concentrate mainly on the tests that assume population centers are identical, which means we assume the two samples have equal means or equal median at the same center, or they have different median, but there is a difference, there's a gap between the median. By subtracting this gap from every observation in one sample, we can make the two sample have the same median. Or in other words, they either have identical median or we can make them to have identical median by an addition or a subtraction from one set of the sample values. So it's difficult to develop completely distribution-free tests for variance. It's somehow it's not totally computational free, because when we subtract the difference from the observations of one sample, we kind of accept they have the same shape, right? They their center is just that they have different center, so we add a value or deduct a value from one sample, then they have identical center. So let's learn another test based on the F-test, but this time is for the nonparametric methods. It's called Siegel-Tukey test. So the test is based on Wilcoxon-Mann-Whitney test. we change the WMW ranks to test for scale comparison. So how does it work? We first combine the two samples again as one big sample, then arrange the ranks like this, arrange the joint ranks like this. We allocate rank 1 to the smallest observation of the one combined big sample, and then rank 2 and rank 3 to the largest two observation. Then allocate rank 4 and rank 5 to the next two smallest, then rank 6 and 7 to the next two largest, and so on. So this is to rank the observations. We first put all the observations in two samples in ascending order. Then we rank them from the tail to the middle and end up in the center, right? Then after that, after we have ranks like this, we can perform the WMW test using the these ranks. So let's look at an example. 11, two types of tire failure under similar test conditions. These are the times to their failure in minutes. Oh, sorry, the unit is in hours. So how many hours till failure? And there are two types of failure, type A and type B. And these are the, we apply WMW as described. So it's two-tail. We want to test if the variance in their time to failure are equal. So it's two-tail, whether equal or not equal. So first we need to check if the two samples have similar medians. If they do, then it's okay, we don't need to do anything. If they don't have the same median, then we need to add to or subtract from the difference on one sample to make them have the same median. So it seems the first sample median is 231, whereas the second sample median is 184.5. There is a 46.5 gap between the two medians. Therefore, to make them have the same median, we use every observation in sample A to subtract this difference. And then we get the new sample A, new sample 1, type A. This time, these two samples have the same median, so we can perform the variance test. Then, using the method we introduced to rank this data, first, the one combined big sample in ascending order is marked as value in row 1 and row 3. And then we do the rank as the smallest rank 1, the biggest rank 2, the second biggest rank 3. Then the next smallest 2, rank 4, 5, the next biggest 2, rank 6 and 7, and so on. And we end up in the middle. This is rank 20, this is 19. So given we have this rank, we can compute the sum of the ranks SM as 106, and UM using this equation is 7. Given SM and UM, we can perform the WMW test, right? In R, we don't even need to assign the ranks like this. We just need to input. We need to, if we use Wilcox test in R, we still need to manually allocate the ranks. When we have the rank of the two samples, we need to separate sample 1 rank, sample 2 rank, and then input those ranks here as two numeric vectors. Then run the Wilcox test. It will give us, this is the UM, right? And then this is the p-value. So the p-value is just above 0.05, so it's not strong evidence against the null. Although it says the true location shift is not equal to 0, it seems it's testing the mean. However, we actually convert the variance, convert the spread as the ranks here. And by checking the location of these two vectors, these two ranks, actually we are comparing the spread of the two samples. So the conclusion is actually about the variance instead of the location, right? Because the p-value in this case is not smaller than 0.05, there is weak evidence against the null hypothesis. We conclude the two samples have similar variances. But if you don't adjust the median, if we use the original value by ignoring the difference in their medians, then the p-value would be 0.0268, which is very low, which allows us to reject the null. Totally different conclusions, which means to adjust the median to make them have the same median is very important to the test, right? So as long as we have joint ranks, we can use any program that runs WMW test to run this Siegel-Tukey test, right? All right, next we introduce another test for variance. It's an Ansari-Bradley type test, or AB test for short. A new test statistic named AB test is developed for this test. We rank all observations from two samples in ascending order. Then we get a DI. DI is calculated like this, is the ith observation. This is actually its rank, right? Because it's already in the ascending order. This is the joint rank. Use its joint rank to subtract the half of the combined sample size plus 1. This actually measures the distance between an observation and the center, the middle ranked observation. How many distance in terms of the rank from observation to the middle rank of the observation. So this is the meaning of the AB statistic. So, and then given that the AB scores is actually the absolute DI, absolute value of DI instead of DI, because DI can be positive or negative, but what we care is only the absolute distance between an observation and the middle ranked observation. Therefore, we only use the absolute DI as the test statistic. So 612 example 612, we still use the two-type tire failure data in the previous example. Then let's see how to use this AB test. So again, we have combined them into one big sample and have the joint ranks just as regular, from smallest to the largest. Then we get their DI or their score, AB score. For example, the middle one will have very low absolute DI, right? Because they are right in the middle. Their DI is low. Then the more farther away from the center, the more far into the tail, then the larger DI they have. So given all this DI, and it's symmetrical, right? The first item is 9.5, the last one is also 9.5. Then we can calculate S. That is the sum of these scores for one sample. given this S, we can perform the test and it will give us the p-value. So using R, there is a function especially for the A/B test, Ansari dot test. And in this test, we don't need to manually assign the DI, the score, to the observations. We just need to input the two original sample measurements, but remember to subtract the difference between their medians manually like this. This will make the two samples have the same median, right? And it will return us the p-value. All right, so there is little evidence against the null hypothesis because p is large. Using the same data, the p-value from the Ansari-Bradley test is slightly greater than the p-value from the Siegel-Tukey test. So here are some more descriptions about the Ansari-Bradley test in R. So here is the where am I? Okay. Then next test, we will only introduce the concept of this test, but we will not show any example. So this is another test to test the equality of variance between two samples. It's called Canova squared rank test. Why do we have different methods for testing or estimating the same parameters? Because each method has strengths and drawbacks. Based on the features of our problems, we may select the most appropriate method, or we can try multiple methods to test the one parameter. For example, for just now, we use the same data to perform the A/B test and the Siegel-Tukey test, and they have different p-values, right? For the Siegel-Tukey test, the p-value is lower, although they give us the same conclusion, not reject the null. Still, if there we need some tendency to be reservative, to tend to reject the null more, then we may choose the Siegel-Tukey test. Otherwise, if we want a test that give us a higher p-value to not to reject the null as possible, then we can choose the A/B test. And for Canova square rank test, because and also even we don't know the features of our data, we don't know which method is the best one, is the most appropriate one, we can perform multiple tests and get different results and conclusions. And among those results and conclusions, we can choose the best one from them, right? So Canova squared rank test, we will skip the example. We just introduce how it works because variance is the square of standard deviation. The unit of variance is the square of the unit of the variable, right? So it makes sense to have a square rank. Canova Canova is a person, and he proposed a test for variance based on the joint squared rank. First, we get each observation, observation's deviation from the sample mean, which is to use each observation to subtract the sample mean. This sample mean is not the mean of the big combined sample, but the mean of each separate sample, right? Sample 1 mean, sample 2 mean, and it's the mean that score we use T to denote it, and it's the test statistic of the Canova square rank test. And with the mean and variance of the t, we can convert the t value to a z value and use normal approximation. So let's give the example. You may read it in the textbook. And let's continue. Testing if two samples have a common distribution. So before we talk about testing center, testing median, mean, testing the variance, and to test the distribution type or distribution family, it's like to test if two distributions have similar shape, right? So this time we introduce Smirnov test. You may heard of the term Kolmogorov-Smirnov test, KS test, when we learned chapter 4, when we want to test the distribution of one sample, right? In R, it's the KS dot test. It's this one, KS dot test. So Smirnov test can also be used for two samples. It has similarities with the Kolmogorov test. Remember Kolmogorov test? We use the sample cumulative distribution function, the big Sx, right? Use that plot and identify the biggest magnitude from that Sx to the CDF, right? Use the biggest magnitude, we determine whether a distribution is equal to what we guess. So for two samples, it's the same. We perform the Sx for both samples and identify the biggest gap between them and use that biggest gap to determine whether the two samples have the same distribution. Then example 615. The following data are rates of saliva production for female and male. And the unit is ml per minute. So 7 females and 21 males. Do they have the same distribution? So first, compute the sample accumulative distribution Sx for sample 1. We name it S1x, and sample 2, we name it S2y. And remember, that is like stairs, right? Each step is 1 over its sample size. So for this example, because female sample size is only 7 and male is 21, so one sample step is much larger than the other, right? However, this is the data we have, and we have to use these two samples with big difference in their sample size to determine the distribution of two populations. So we use a table to list the real measurement data of the two samples and then the Sx of these two samples. Because female has only 7 observations, male has 21. Therefore, it means to compare S1x and S2y, we have to replicate it a lot of Sx in female group, right? Then there are a lot of repeated values here because the sample size is small. That's the way we have one value in female corresponding with one value in male that we can get the difference between S1 and S2. So using this table, we can get the greatest magnitude as 0.524. This column is the magnitude of the two Sx, and the greatest value is here, 0.524. So use this greatest magnitude, we can determine whether we use two-tail one is provided in stat exact, gives exact one-tail p-value as this one. So the two-tail p-value is this one. It's weak evidence against the null. So we need to conclude there's not a obvious difference in variance between two genders, Salva distribution. Okay. So, however, the test may be lack of power, right? Because the sample sizes are so different. The sample size for female is too small. And we know that Kolmogorov works better when the sample size is large. So we can use KS test in R for the Smirnov test. We just need to input the two data sets like this, right, without any further calculation. They're just the two original measurements of this data. And then they will give us the biggest magnitude, biggest deviation between S1 and S2, then a p-value. And the conclusion, however, in KS test, we're not using the sample cumulative distribution function. We're actually using the CDF, the cumulative distribution function, which is an asymptotic result. So more descriptions about KS test. All right, and something we need to skip. Then let's do a summary. There are a wide variety of application fields for the two independent sample problems. Not only limited to these fields here, right? So in medical field, we can test the efficacies of two drugs, two treatments, and so on. One group using one new drug, and the other group just use the regular old drug, and so on. In sociology, we may evaluate the fitness in town or country, or compare the effectiveness of two policies, compare the performances of two schools, of two exams, right? Two training, one training, one group take the training, the other without take a training, right? Studying the causes of some certain group's action. And in mineral exploration, we may test the median or spread of two sites. In manufacturing, we can compare two processes or vendors. Their performance include their center, their spread, and their distribution. In psychology, learning with a treated group, compare the test group with the control group, and so on. And you can add a lot of more applications in education, in social media, in a lot of different industries, as long as we want to compare two things, we can use these two independent sample problem methods. So in summary, in chapter 6, we learned how to use, learned all the problems dealing with the two independent sample problems. We compare their centrality, compare their median, compare their variance, and compare their distribution. First, we learn how to use WMW to perform a two-sample test for the median. And then we introduce 3 ways to test the equality of variance for two samples. They all have one assumption that the two samples have the same median, or can have the same median by subtracting the difference from one sample. And the 3 methods include Siegel-Tukey, Siegel-Tukey, which is setting ranks from the tails to the middle and use the sum of ranks to do a WMW test. Then Ansari-Bradley type test, AB test, which is giving a score absolute DI to each observation, and DI is a function of I and combined sample size. So in the middle, the DI is lower, and in the two tails, the DI would be larger, right? And DI is symmetric. Then use the sum of the score to do the test. And then the third method is Canova squared rank, using the square of the deviation to rank the observations, and then use the sum of the squared ranks as a test statistic t and convert it to z value and use normal approximation to do the test. And then we introduce a Smirnov test to test the distribution of two samples, and we skip this one. So this is the last chapter that we have homework, and it has only 2 problems. And some students ask me for problem 6.2, there are only letters without real value. How do we do that? So the hint is, the hint for problem 6.2 is to make a table like example 6.7. And then for 6.5, then the hint is use our function P Wilcox. All right, and then I will quickly go through chapter 7 and chapter 10 in this week, and early next week, I will post the slides for chapter 12, but no lecture video for chapter 12. Then our exam, our final exam will be open notes, open textbook, open programs, open computer, open everything. Because this course, we require a lot of coding and programming, not a lot, but we do need some functions in R to do the test. But we still have some manually calculation problems. You need to know the basic concepts, ideas, and mathematics behind each method. So for our final exam is mainly about chapter 1 to chapter 7. And there will be a lot of homework problems, exactly the same in final exam. And that's all.